Hello everyone. This is Aishwarya. I'll be the moderator for the event. And today we have Ashley Varghese with us to enlighten or give a technical talk about leveraging novel computer vision and machine learning solutions for visual inspection at Canadian National Railway. So I hope you have been enjoying the whole conference so far. So to give a short bio about Ashley, she is a data scientist at Canadian National Railway. She works in the automated inspection program, overseeing the development and retaining aspects for the inspection of rail cars. She has over 10 years of research experience in computer vision and deep learning. Her research papers are published in multiple international conferences and journals. She has previously worked as an AI scientist at Industrial Skyworks and as a researcher at the TCS Innovation Lab. She holds an MTech in computer science from the National Institution of Information Technology, Bangalore. So amazing, Ashley. We are very eager to hear about the technical talk you'll be giving today. So I'll be handing over it to you, and you can go ahead.
Thanks, Aishwarya. Good afternoon, everyone. My name is Ashley Varghese, so I'm a data scientist at Canadian National. So it's my privilege to be presenting some of the recent work that CN has been doing to improve the overall operating efficiency through automations by leveraging computer vision and machine learning. So, as we would all know that Canadian National Railway is one of the dominant rail transportation and logistic companies spanning from east to west coast, covering the United States and Canada. So we have around 23,000 railroaders working round the clock to ensure that all essential goods and commodities reach the right parties on time. Over 20,000 miles of railroads using close to 100,000 rail cars operate on these railroads at any given day. So the overall operations do come with complexities owing to varying seasons and weather conditions across the geography. CN has one of the organizations which realized the importance of AI and adopted some of the latest technologies in railroad operations. So we at CN have been evaluating and adopting some of the latest technologies to automate the operation of rail cars and ensuring that operation effectiveness increases by use of digital techniques and analytics. This is leading to make the whole organization more effective. So things that record days, if not months, get done in matter of hours. So, and the workforce that required earlier to accomplish a task is reduced to a small fraction of that. So it is right to claim that CN has become more agile and effective as an organization, and also all this process is resulting in higher revenue growth and return of investment. These are some of the ML projects that CN. So the workflow is very simple. First, we leverage ML for making meaningful predictions from the data that we have, and using these predictions to plan on optimal operations. And planning of these optimal operations results in better managing uncertainties and thus ensuring high effectiveness. So it's like predict, plan, and manage uncertainties. So in these ML projects, AIP and ATIP are the computer vision projects, and I work with AIP, and today I will be giving an overview of how we mitigate uncertainties with rail cars using digital tools and techniques. Let me introduce to one of our programs at CN before I move to the AIP projects. So this is Autonomous Track Inspection Program. So as I stated at the beginning of my talk, that CN has a railroad network of 20,000 miles. If the track had to be inspected manually, the whole process would take a lot of time and it's prone to human errors. So now think of a scenario like we are taking a rail car and load it with the cameras and other sensors and bundle them with digital tools and techniques. And we put this in between rail cars and let it run in a regular train. So this special car is enabled to do digitized inspection without any intervention from the humans. So there are like many sensors in the rail car. So this is one of the 3D scans. So this for inspecting different rail car components, and there are different sensors that measure the track geometry, like the distance between the rails, the height and width of the rails, and the lidar point clouds are generated to get like other information like the track clearance, vegetation covers, and this is one of the images that are used for finding the missing board. And ATIP has been awarded the prestigious Railway Association of Canada's 2021 Safety Award. Now we'll move to the track, move from the track inspection, the car inspection. Let us look at a traditional approach for rail car inspections. So we can see here in the diagram that the train reaches the yard and undergo an inbound inspection is called certified car inspection, CCI, and it's a regulated inspection. And there would be like two to three human inspectors. They inspect the rail components, and it would take anywhere like between 2 to 3 hours for inspection of a single train. So once done the inspection, then it goes to the classification bowl and decouple the defective rail, and then it's sent to the car shop for the defect fixing. And the rest of the trains will move out to the yard, and there would be the final inspection process. So that is called rolling departure inspection. Like the train would be moving and rolling out of the yard. And here the two inspectors would be standing the left and right of the train and would be inspecting some of the components during the during the train would be exiting the yard. So, like we all know that Canada is a cold country, and if all this inspection has to be carried out during all seasons, and it takes a lot of time. So, how do we solve this problem? So, in one of the slides earlier, like we saw that like there is a car loaded with the cameras and sensors, and we use that technique to detect the track. So now, like, how about putting all this in a portal and letting the train pass through that portal to detect the defects on the rail car? So the data capture is done when the train is in a motion. So there is no delay, and the digital technologies ensure like safe, consistent, and reliable inspection process. So here the human bias is eliminated. So the benefit is to reduce the inbound inspection time, and we want to remove the rollback inspections. So moving on to the next slide. So this is a picture of an inspection portal. Uh, these portals are equipped with two generations of cameras that are positioned to capture all sides of the rail car, including the undercarriage. Like there are cameras in the track. Once these images are captured, these are sent to the servers at the site to process, save the images, and send it to the AI inference engine to identify the defects. Uh, so once we collect the data and the inference, the inspection report will be sent to the yard. So the yard is away from the inspection portal. So by the time the train reaches the yard, the report would be ready, and the mechanical team can do the maintenance operation immediately. And these are the images of a single car captured by different cameras at the portal. So these are the images from 5 different cameras. So this is the side view, and this one is the little lowest portion of the same car, and this one also is the same, but it's a different side of the car. And this is the top view, and this is the undercarriage view. And we use these images to detect like various components and the defects of the rail car. And these are the few Gen 2 camera images. So it's from the same car. So here you could see like it's more component focused. So here we could see that components more clear, and these are like high resolution images. This would be mainly used to find the defects like cracks, missing bolts, or some of the components at the end of the car and it's not visible from the side view camera. So these cameras are fixed at like perpendicular and oblique angles to the car and make sure that we will able to capture all the components we require. So before I go to this ML solution, so first I would like to give an overview of what is an use case. So we are like I'm going to explain everything in terms of the use case. So use case is like a inspection task, and the whole inspection task we divided into many use cases, and each use case defines the defect detection of a single or multiple components. For example, finding a defect of a brake beam is a one use case, and finding a defect of our operating lever could be another. So, like we simplify the inspection task into multiple use cases, and every use case has a lot of different operations. I will go into more details about in the coming slide. And this is the use case life cycle. So we start with defining the scope of use case, then data collection and labeling. We design a pipeline, model training. So once it's done, we evaluate the performance of individual models and the use case. And then we deploy the model in production and we validate and monitor the performance. In this pipeline, this may not be a single iteration because your in the first iteration your performance of the use case may not be good enough. So you need to keep like train the models and change the pipeline. So it would be in a iterative mode. So I will be going in more detail into each of these components. So first, scope of use case. So this is the first step in the process. So the subject matter expert, like SME of a like he is very familiar with most of the components in the rail car. So that SME provides like various details like location of the components to be inspect, how it looks, what it does, and how to distinguish the defective and non-defective components. So here in the picture, you can see there is a lever, and this is a lever with a handle. This handle is non-defective, and here this is the broken handle. So this would mark it as a defective. So once we get this kind of specifications, then we need to identify which camera source that gives the best view of the component, because like the same car, different cameras would be capturing the image. So we need to identify the camera source that gives the best view. So sometimes it might be a single or multiple use camera view images required for a single use case development. The next step is like data gathering and labeling. The main aspect of data gathering is to collect as many images of the defective component as possible. So more the sample of defect, the better would be the outcome of the solutions. Once we gather all these images, we have to be labeled properly. I think, as we all know, that the label should be consistent. I think that is a very important aspect of this whole process. Labeling is a time-intensive effort. However, like we would all agree to fact that better the labeling, the better the overall accuracy of the model. During this phase, actually we analyze the data and come upon the labeling strategy, like how many classes to be categorization, what should be the class label, how to label. So everything depends on the use case, like what is the outcome we want. So I put this picture with a purpose, like because here in this use case we want to detect this lever and identify whether it's the bend or not. So one of the way of labeling this one is like drawing a bounding box here and see, okay, it's the bend one and this is not bend, like something like that. But if you look at this picture, you could see like there are a lot of bars in the background. So if you label only this one and train your model, the model may get confused and it affects your model performance. So one of the strategies that we use, that we decided to include the handle also, because that gives more unique features compared to other components. So like these kind of strategies we try to bring up during the labeling phase, that will ensure that it generate a unique feature space that differentiate that object from the background. The next one is like we design a machine learning pipeline. So pipeline is nothing but a sequence of machine learning and non-ML tasks that defines the workflow. So it's an executable workflow, and we can run this and generate some results. So it, like for example, this is an sample pipeline. So you give an image. So as you have seen, like uh, the images that we get from the portals are like long images, and sometimes your object of interest is small compared to the image resolution. So we may not, we won't able to directly send that image to the model for training. So in that cases, we need to slice the images. So for that, we move a sliding window and generate the tiles, and then those image tiles will be sent for the training. So this is one detection model and detecting sliding and pneumatic gates. And once you get the results, like as there are many tiles, you will be getting a lot of boxes. So we apply non-maximum separation to remove all overlapping boxes. Then we can have like a lot of different conditions, like everything is based on the use cases. Then here there is a classifier. So like overall, like a pipeline consists of a lot of series of operations, and these are the model inferencing, and it could have like a single or multiple models, depends on the use case complexity. And some of the general operations that we use in the pipeline is like from the ML side, like object detection, object segmentation, and classification. And like we use a lot of image processing algorithm to improve the enhance the image and improve the performance of the model, like histogram equalization or image slicing and ROI selection, etc. Uh, Let us look at some of the sample use cases that will give you an idea, like what are the different type of computer vision algorithms to be applied to find the defects. So here there are is the images of 4 use cases. So these green bounding box is the non-defective, and the red one is the defective. So this is first one is like retainer valve detection. So if the valve is pointing down, then it's non-defective. If it's pointing in some other direction, it's defective. Similar one, like here you would be looking at whether this valve caps are open or closed, or this gate door is open or closed. So these are like you can train a model and like detect this component, then you can have a classifier to classify whether it's open or closed or a defective. This use case is like you have to find a broken beam, break beam. Here, this one is slightly trickier here because there is a thin bar and there is a here it's broken. So for this kind of use cases, we have to ensure that the model trained properly. Like generally, we generate generate heat map and see whether it's focused on the right location instead of learning from some other objects in the background. So these are like kind of law complex use cases, but when it comes to this one, here there are like, you need to identify, is there any missing lever? And actually these are the images of the same location of the card, and here there is a lever, but here there is no lever. So many case these kind of scenarios, like you cannot simply train a model to find whether it's the lever is present or not. So here we may need to add like extra logics or like a lot of other logics along with the trained models to come to a conclusion that the lever is missing, or like here another use case is like a missing pin, and this one is like the brake applied, it's a air brake or a hand brake, so that is decided by the width and height ratio of this piston. So these kind of use cases, we need to go for measurement, and we need to calculate how many pixels are there. First you identify the component, then you need to measure to the mission, and you have to, so all these use cases, like you have to add like extra business logic to come to a conclusion whether the component is defective or not. So after we went through different type of use cases, so there are like many challenges in the data, like if you want to train your model. So one is like subjectivity, like subjectivity, like here this one is bent and this one is slightly bent, like as per SME this is not defective and this one is defective, like this kind of subjectivity comes. Another challenge is like, it's like a very common one, like the number of defect samples would be very less, so always it would be like an unbalanced data set. And in the same components you may have like different variations. So here this is a lever, but the shape of these levers are different, like these are like type 1, type 2, type 3, like there are different type of levers. So when we train the model, we should make sure that it's able to detect all the component variations. Another challenge is detecting thin and small objects, like if pin is missing or a bolt is missing. So how to handle these kind of cases. And there are scenarios like your object of interest is obstructed by another component. So these are the main challenges. There are a lot, but these are the few things I would like to point out here. So when it comes to training models, so like we need to build a model that gives the best performance in detecting rail car components and defects. So the approach CL took is very simple, like we get a deep learning, work in tandem with machine vision to automate the process of inspection. So we mainly use deep learning based techniques. Is computer vision technology is used for automation of this visual inspection. So we use convolution neural network architecture, like many state-of-the-art convolution neural network architectures used for different computer vision tasks like object detection, classification, and segmentations. And even various image processing algorithms also been applied on this to improve the model performance. And when it comes to the rail car data, the augmentations need to be chosen carefully because all the general augmentations may not be applicable. So we, like every use cases, we have to design its own augmentation techniques. And there are like at the end that whole inspection process, like we be using many architectures and we would be comparing the performance of each network. But at the end, like it would be like more into a data centric approach. Like most of the times we observe that the model performance improves better, like as we improve the quality of the data. And these are the different modeling techniques that we generally use for different use cases. So deep learning based, we have this detection, segmentation, classification, and some of the use case we use OCR, SVM, and then non-machine learning, like sometimes we need to use the measurements for edge, identify the edge, then we have to go for the measurement. So once we train the model, the next step is inferencing. The results from all the models are aggregated and applied business logic to conclude like whether the components defect. So from your model, you may get an output, okay, here there is a lever, it's good or a bend, or like here there is a handle. But this one is like a same lever got detected from different frames. So at the end, we need to choose one conclusion, like a one box. So for that, like we may need to have like add extra logic, like which one is predicted more. So there could be a scenario like in this frame, it would have told that okay, this is bend, and from this frame, the model would have predicted it's a good one. So then how do we choose, like if you have like different layers are predicted for the same component? So we need to add like a lot of extra logics to come to a conclusion that it's bend or not. So every use cases we had this kind of logics, and finally we come to a conclusion. So once we finish the use case, then we do the unit testing and we evaluate the model performance and the pipeline performance. We use various metrics like precision, recall, F-score, and we compare the performance. And once the pipeline meet the targets, then we send it for the deployment, and the QA team will test it, and finally the model will be in the production. So far, CN has deployed like more than 50 use cases into production, and this is the GUI of the inspection portal. Like this is what there is a validation team, so they would be validating the results from the model. So this is the GUI, and here you would be presenting all the results like for this train and this car, and we found that there is a valve here and it's not defective. So here the validation team has the option like whether this result is correct or like valid or invalid. So here the inspectors can validate the results. So, so far we just went through all these phases of this use case. So like again, like we define the scope, labeling, then training, we validate the performance, then deploy, but the performance of this use case in productions are monitored, and we would be keep monitoring, and all the invalid data is collected and sent for retraining for improving the modeling from model performance. So it's kind of a cyclic process. Then like collect all the invalid data and send it for retraining. And again, it goes for the model training. During retraining phase, most of the times we don't want to go back again to the ML pipeline because we would be mainly focusing more on the improving the performance of the model. So just lay to the data, training the model and test the whole pipeline again. So as I mentioned in the previous slide, like the learning does not end in one iteration. It's a cyclic process, and the model needs to be trained till it meets the required targets. So we could efficiently improve this whole process by adding few steps like The first one is choosing the best data for the model training instead of pushing all the data we collected from the portals. And the second one is like enabling auto labeling to auto label some of the components based on the existing model in production. So like here, like enabling this active learning mode that compares the label data distribution with the unlabeled samples and removes samples that are too similar to the already labeled data. So that would improve the performance. So definitely there is a human in the loop. So to ensure that the data that goes to the model is accurate. So just for ensuring that data quality, there would be a human in the loop. These are some of the like roadmaps going ahead, and thank you all. Thank you all listening to my presentation, and I would like to take this opportunity to let interested people know that like we would have position open up for ML developers and specialists in the near future. So if interested, please connect with me on LinkedIn. Thank you all.
And thank you so much, Ashley. I really appreciate that. I hope you enjoyed. I hope the folks that have tuned in have found this very helpful. There was a question here. Can you see the chat session questions?
Yeah.
Just go. Okay, if you just go on the right side in the session tab. Calvin had mentioned, huge fan of railway cars, got me through COVID in Canada. Yeah, that was the distance traveled in Canada. If you're not taking, that's interesting. You know what? Could be a good next vacation destination. How many samples per defect class were used to make the model sufficiently accurate? Moreover, what technologies were used to help with labeling? Was one of the questions.
Yeah, so as I mentioned earlier, like collecting a defective samples, it would be very difficult, like always the number would be less. So normally it would be in hundreds during the use case development, and during the retraining phase, like we will collect more data and keep updating the model. So I could say it would be in few hundreds, and in the retraining it may go up to few thousand. For the whole data set, not the defect class.
Kelvin asks, can you walk us through the human in the loop experience and how does it impact product timelines or costs?
Yeah, so the slide that I presented, the last one, like that is not, we have like some of the things that we plan in the future. So we don't have, like, we have not yet start, like it's in the phase, like we are just working on it.
Thank you. Alireza asks, how many computer vision models do you have in production? And then just generally, does the organization trust in those computer vision models, or do you have a lot of trust in those computer vision models?
Yeah, definitely. So whereas like more than hundreds of models are in the production, so as I mentioned, like every use case may have like multiple models. So there are like hundreds of like more than 100 models. But like we would be keep checking the performance of every model, and some of the models are performing very well and like it's completely in the automated mode, and some of them are not performing well, so that we go through the retraining phase and we just keep going through that iterations again and again to meet the target.
Thank you. That's interesting. Fatin asks, with the size of data set, what kind of data augmentation was done? What techniques to maximize efficacy of model and small sample set? Sorry, efficacy of model with small sample set.
Okay, the size of the data set, I said like it would be a few hundreds, and there are like various, we use like normal standard augmentation techniques like flip or a vertical flip, horizontal flip, rotation, shift, or those kind of augmentation techniques. So one of the things like it depends on every use case is like how how we augmented the data, and we make sure that we won't always get a balanced data set, but we'll try our best to get kind of a balanced data set. And also when we do the augmentation, so we make sure that like we don't repeat the same images again and again. Like we try to bring some like variations of what are the possible variations that we could think of in that use case.
Thank you. Shreyash asks, great presentation, Ashley. Question, you said that you had a data imbalance. Which methods have been most effective to fix that?
Like for handling the data balance, so most of the times, like one of the way of doing is the augmentations, and or we try to just adjust the number of labels in each class to get an imbalance, get a balanced data set. But like it won't be like always, it won't be a balance. Like in many cases, it would be an imbalanced data set.
Zarina asked, and I hope I'm pronouncing that right. How long did it take to complete for this use case cycle? By the way, thanks for the informative presentation. Actually, much appreciated. Yeah, so how long did it take to complete for this use case cycle?
Okay. So for this use case, we have like two different cycle. Like one is the development phase, another one is the retaining. So development, like usually it will be like 4 to 6 weeks. Like again, it depends on the complexity of the use cases. Like if it's a complex use cases, it can go up to 8 or 10 weeks.
An example of a company that I don't think would be sort of digital, or forgive me for my naivety, but data first, right? We think of like the FANG companies, and then the other side, we think of like a traditional means of transportation, rail, right? So what went into trying to take a lot of this data just from the onset, digitalize it, or just get the team sort of thinking, or even the stakeholders, the business sort of directors thinking of how these benefits might be laid out, right, for them? Because I know that speaking with so many companies, it's such a challenge to get sort of an organization, even from a directorial level, the board, to think of the potential and possibilities of machine learning. And you guys seem to have done that really, really great. Is there any information that you can give us as to like the method it took to get to this point?
Yeah, I think I think it's a big change, it's a big leap in the organization. One of the projects I presented at ATIP, so it was like one of the very successful projects, and that project we could replace a lot of like manual label with automated solution, and like we could get more defects than the manual inspections. So it definitely improved the overall operational efficiency of the organization.
Thank you so much. Well, that's I think that's good for the questions. I mean, this was fantastic, Ashley, and I want to just thank you for sharing, for having permission for CN to be able and willing to allow you to share this. It's very nice. I know that you and your team have attended the events throughout the past, and it's nice to have you present for a change. So thank you so much, and I hope this is just the beginning.
Yeah, thanks, David, for giving me this opportunity, and thanks to my team. I think my team also joined this presentation, and thanks to CN.
You're most welcome. And Alireza, just so that you're aware, if you go on the replay side on the left, after the sessions, we'll be uploading those so you can replay them. With the exception of very few, we're able to do that. As well, we will do some light editing and be making the videos. I think we'll post those on YouTube and give everyone the link for that as well. So stay tuned for that. If you want to immediately watch it, it should be in the replay section very shortly, okay?
Okay.
Also, yeah, thank you, Ashley, and thanks everyone for joining, and we'll kick it off here and join for the other sessions.
Yeah,
See you in there.
Thank you. Thank you,
Thanks.
Steve.